Okay, good morning. So, if you remember, we had some problems with one of our understandings related to the interior angles, the sum of the interior angles of a polygon. If you don't mind, let me start a fresh lesson today. But at the end, we will go. Probably we get some time to think about it again. And then I also gave you one problem. I don't know how many of you managed to solve that. Okay. We also probably will get some time to look through it. So here, this is also a very simple and very important lesson, congruency of triangles. So two triangles are said to be congruent if the sides from one are equal to the sides of the other one, and the angles of one are correspondingly equal to the angle of the other one. Yeah. So in principle, you have two copies of the same triangle. If you have that, that's called two congruent triangles. So congruent triangles. So I don't know, it is hard to draw congruent triangles by hand, but I will try to do my best. So if this is your triangle, let me call it ABC. And then I have another triangle somewhere else. A prime, B prime, C prime. Do you have any problems with this notation? So A prime, B prime, C prime just means that different points, yes? That's common in geometry. I can call them M and P. It's better to call them A prime, B prime, C prime. So somehow it actually transfers this idea that A and A prime are somehow corresponding to each other or something like that. So these two triangles are said to be congruent if I have 6 conditions satisfied. Yes? For example, the length, here I mean the length AB is equal to the length A prime B prime. So let us just represent it by this dash. And then AC is equal to A prime C prime. And BC is equal to B prime C prime. On the other hand, the measure of the angle A should be equal to the measure of angle A prime. The measure of angle B should be the measure of angle B prime, and the measure of angle C should be the measure of the angle C prime. So I would say this A and A prime are the same. From size point of view, this B and B prime are the same. And finally, this C and C prime are the same. So you can imagine that I have one of them in paper. I put it in the copy machine and copy another one. Those two triangles are congruent triangles. But of course, I have drawn them in a way you don't have to do it. For example, you can imagine you have this type of triangle this way. So let me call it A double prime, C double prime this time, B double prime. So if I can really draw them so that the length of A double prime, C double prime is equal to AC, the length of A double prime, B double prime is equal to the length of AB, and so forth. These two triangles are also called congruent. So if you want, you can imagine it in this way. Two triangles are congruent if I can do some transformation on one of them so that it goes and completely overlaps the other one. Yes. So for example, here I can just translate it here to put it on top of that. They should exactly overlap each other. Here, of course, if I have a triangle like this, so here, just translation is not enough. I also have to rotate and translate. Yes. Here, even rotation is not enough. Yes. I have to reflect it. So here you see, if I start rotating it around or translating it around, I will not be able to put it exactly on top of this. So I need another transformation, which is a reflection. Yes. So I have to, for example, take it out from 2 dimensions and reflect it in the 3rd dimension, put it back here, and just try to see that they overlap. But let us not make things so complicated. Everyone understands what's the meaning of congruent triangles, right? So in principle, by definition, I need 6 conditions to be met in order to conclude that these two triangles are congruent. In that case, this is the symbol we use. This is the notation we use. We say triangle ABC. The congruency notation is this symbol. And then I write triangle A prime, B prime, C prime. If you want to be strict, you really need to have to pay attention to the order. Yes? This is the convention that if you write ABC as the name of your first triangle, you have to respect the order on the second one. Here by order I mean that if you have chosen to write A, write the corresponding vertex for the second one. If you have chosen to put B in the second place, write B prime in the second place, because B and B prime are equal angles. C and C prime are equal angles, and A and A prime are equal angles. Even though sometimes I myself will be sloppy and don't follow the rule, but this is the convention usually, especially if you see a written text problem. If they are using this in principle, they are using this convention. Okay. And then, by the way, so you have this feeling that if I have two congruent triangles, any other part of the triangle from one should match with the corresponding part of the other one. Yes, for example, I don't know, if we call this the height AH, if I know that two triangles are equal, then of course if I draw the corresponding height from the other one and I call it A prime, H prime, if I know that the triangles are congruent, then I can also conclude that, for example, AH, the length of AH is equal to the length of A prime, H prime. Yes? Okay. And then it turns out that we really don't need to check all these 6 conditions out to conclude that two triangles are congruent. Some of them are enough. Actually, 3 of them chosen in a wise way is enough so that you can conclude the other ones. Yes?
Okay. So, when you said that we're allowed to do transformations,
yeah,
and you said we're allowed to do scaling.
Mm-hmm. I didn't say scaling.
Okay, so
yeah. So if you want, I have to check isometric transformations. Isometric transformations are those transformations that keeping the length the same.
Okay.
Mm-hmm. And reflection, rotation, and translation are among isometric transformations. Okay, but that was a good point. Thank you. So here we also need to add one axiom. Okay, and that is called let me write it like this. So axiom, this is an axiom, so it means that this is a statement. It seems natural, but we don't have a good proof. We don't have a proof for that based on the previous statements that we have. Yes. So axiom, I would call it SAS. This is side angle side congruency of triangles. Okay, so before continuing, let me just clean this here. Let me just draw one more. So if I have this triangle, so always consider that I can draw precisely the same picture, which of course I can't, but let us pretend that they are actually really the same size and everything. So A prime, B prime, C prime. So assume that my goal is to show that these two triangles are congruent. Yes, in principle, I should check the sizes of 3 sides from this and the sizes of 3 sides from that. They have to match, and I also have to measure all the angles. But for example, you can immediately realize I really don't need to check the third angle, equality of the third one, yes? Because we know that the sum of the interior angles of triangle is 180 degrees, if a pair of them matches with a pair of the other one, automatically the third one also matches, yes? So for example, you see that we really don't need to bother about this. Okay, we can do more than that. Instead of 6 of them, I select actually 3 of them in a wise way, which will guarantee the other 3. Yes? One of them is the content of SAS congruency, and this tells you that if 2 sides of a triangle and the angle that are included by those sides, so for example, if AB from this triangle and A prime, B prime from that triangle are equal, if AC and A prime, C prime are also equal, so assume that someone tells me that this length is equal to that length, and someone tells me that this length is equal to that one, and someone also tells me that the angle that these 2 sides include, angle A, is also equal to the angle A prime that these 2 sides include. So if you see, from these 6 conditions, I have chosen this, I have chosen this, and I have chosen this. I don't check the other ones. So for example, here it is not trivial that B should be equal to B prime, C should be equal to C prime. What we can be sure is that the sum of B and C is equal to the sum of B prime and C prime, but why they are individually equal is not trivial. But I hope that you can agree somehow that it's completely natural that these 2 triangles turn out to be congruent, yes? And this is what I want to consider as the axiom. It is natural. Why? For example, let us try to move this triangle and see if we can manage it to put it on top of that. So this length, according to what you told me, is equal to this length. So I can take this triangle and put it, forget about the rest part of the triangle, I can put it in a way that A prime be on top of A and B prime be on top of B. Yes, that's possible. And now you are telling me that the angle A is equal to angle A prime. So if I want to put the triangle back onto the plane, because the size of this angle and the size of this angle are the same, this A prime C prime lies somewhere on this line, yes? And then because you're also telling me that these are equal, if A prime is already on top of A, and this side is lying on this side, and C prime to A prime has the same length from C to A, then definitely C prime also lies on C. And if they are this, then BC has to be on B. This B prime C prime has to match with B and C. So, but I told you that this is not something that we prove. We actually take it as an axiom. Yes? Okay, and then let me just point something out, that it is crucial that this angle that you are comparing is exactly the angle between those sides, not any angle. Yes, for example, I don't know if we can manage to draw something. For example, let me take this triangle. Okay. So I can let me take it like this. Okay, so consider these 2 triangles so that, oops, sorry. Consider these 2 triangles. Let me call them A, B, C, and D. So that I want to consider this triangle, this bigger triangle. So let me consider this AB, and then let me consider this angle also B, and then let me also consider this angle, let me put one. So let me consider this triangle here, you see, is an isosceles triangle. So let me say that this size is equal to that size. Okay, and now let us consider these 2 triangles. the triangle ABC, ABD, and the triangle ABC. Yes? In these two triangles, you see that AB is equal to AB. Do you agree? Because AB is the side of the bigger triangle, and AB is also the side of this smaller triangle. So they are equal. So this is the side in common. And the angle B is also equal to angle B. Yes? Because this angle B is an angle of this smaller triangle as well as an angle of the bigger triangle. And I myself made this one equal to that one, which is possible, by the way. You can put the needle of the compass here and open it up and just draw some arc so that it will intersect the extension of that. So that's possible. And then I would say that, okay, AC from which one? No, AD from this one is equal to AC from this one. But immediately you realize that these two triangles are not congruent. So you see I have two sides from one triangle, AB and AD. They match with two sides of the other triangle, and one angle of one of them is equal to an angle of the other one. But apparently you see that they are not congruent. Is that clear or not? If you don't see that, let me draw them outside of each other. So I would say that let me take this BC, and for example, let me just draw this 30 degrees, for example. Yes? And then wherever I want, I just connect it here. So this is one triangle, so that's ABC. But let me take this line here, exactly this line. I continue this line, for example, in your head, and then I will draw a line parallel to this one. Yes, no, not parallel. So parallel to this one. Yes, and whatever this is, so that this length is equal to that length, then I will just put the needle of the compass here and then draw an arc. So this will intersect somewhere, and this will give me this triangle. Yes. What I am doing it wrong. Yes. Yeah. So let me go back to this original. Yeah. I'm comparing this one with this one. No, I have to compare the bigger one and this is smaller one. Yeah. So let me just clean that. This is not working here. So here, let me just hatch this. This is the smaller one. AB is one side of this, but now change your perspective and look the bigger one. AB is also a side of the bigger one. So when I write AB from one triangle matches with AB with another triangle, I am right. And then look at AD and AC. AD is a side of the bigger triangle, yes, and AC is the side of the smaller triangle, and based on my construction, they are also equal. Now look at this angle. This is angle in common. This is an angle of this smaller triangle on the one hand. On the other hand, it is an angle of the bigger one. That's also true. So you see that I have two sides from one and one angle from one. They are matching, but apparently they are not congruent. The reason is that this angle that I take into account here is not the angle included by those sides. The angle included by AB and AD is which one? AB and AD. So this is this one. Yes? And the angle between AB and AC is this one. And you see apparently they are not equal. So it is extremely important in this axiom. This is not enough to say two sides and any angle. Two sides and the angle between them should be matched. And this is important to write it as SAS. Side, angle, side. And this means angle between two sides. So that is extremely important to keep the order. Any questions so far? Let us explore some trivial consequences of this axiom. Okay? So let us ask you, what is an isosceles triangle? Can you give me a definition? A very simple one, yes.
It's a triangle with two equal sides.
Two equal sides. Every one of you knows that if I have two equal sides, two angles are also equal. But why? This is an immediate consequence of this axiom. Okay, so let us explore how. So you see, again, let us review how many axioms we have mentioned so far. I just want you to review. There are some statements we didn't prove. 3 of them. This is the third one. The first one was the parallel axiom. So it claims that if I have a line on a plane and I have a point outside that line on the same plane, I can draw a parallel line, and that parallel line is unique. That's the content of that one. And the other one, do you remember what was that? The second axiom, yes?
The axiom of corresponding angles.
Corresponding angles tells you that if you have two lines parallel and you have a transversal, this angle and that angle, which are called corresponding angles, are equal. Yes? And this is the third one that we are using. Yes. So at least we know that which statements we don't have proof for them. So that's good to know. Okay? Okay, now this is the definition, as you mentioned. If I have an isosceles triangle, ABC, when I say I have an isosceles triangle, it means that at least, actually, two sides are equal. And by the way, there is a name for this one. They call it sometimes apex, yes? The vertex from which two equal sides are emitted. Okay, so AB is equal to AC. Of course, I'm completely sure that you know that if AB is equal to AC, then this angle and that angle are equal in size. But why? Because now we cannot say that this is another axiom. We prefer to make the number of axioms as low as possible, yes? We want to be able to prove as many statements as we want, as many statements as is possible. Okay, so if AB is equal to AC, we want to prove that angle B is equal to angle C. Okay, but let me just talk a little bit about this. This is a statement, P. We want to prove if P is true, then Q is also true. This, if P, then Q, as I told you before, it's called an implication. And it is good to know the name of this. That's called premise. And this is called conclusion. Sometimes you can also call it assumption, but the more formal way is the premise. So the premise is that AB is equal to AC. The conclusion, I have put a question mark on top of this implication, is B equals to C. Why is that? So you always use this fact, but let us explore why this is true. Yes?
Because we learned on the first example that if one side and the other side are equal on the other triangle, then the angle.
But there's only one triangle here.
Yes, but we can imagine if they were two triangles.
Okay, so that's exactly but you have to make it clear, because I have one triangle. If you want to really have two triangles, you have to draw a line to make it two triangles. Yes? Which line are you thinking about?
We can draw a line in the middle.
Okay, so that's right. But in the middle, let us see. You see, this is important to understand. What I have to say is that let us take the middle. Okay? But this does not work. If you say I connect it to the middle, let us explore. This is important to understand. Let me call this M. So what Hafsha is saying is that I take the exact middle point, the midpoint between B and C, I call it M, and then I join A to M. Then I will have two triangles. Can you prove that these two triangles are congruent now? Even though they are, but can we prove it? So yes?
Well, we know that Well, since it's an isosceles triangle, we already
Yes, you are right.
yeah,
we
we
know,
know
that this one is equal
yeah,
to that.
and we know that the middle line is equal on both the triangles because it's,
This one.
Yeah, it's the same line, so it's
Yes, that's
equal.
also the same
and
line.
the A on top is also it's split into two equal parts. So
No, we don't know that.
we don't know that.
No, we don't know that. We just connected this to the middle. That's another theorem. It is, you are right. It will bisect it into two equal parts, but that is not immediate consequence of my axiom. Yes?
Well, as we define, or because we defined M as to be the midpoint of BC, we can say that BM and C
Yes, yes.
are equal.
Yeah.
And then by this theorem, we can see that we have two.
Which theorem?
The Sas theorem. That.
This is not a theorem, it's an
no,
axiom.
sorry, axiom.
Yes?
That we have two
No.
two sides which are equal, AC.
No, but I need an
and
angle. As far as I understand, you are not concerned with the angles here. You are considering
yes.
three sides.
Yeah.
One
But
side
it
AB,
wasn't
one side AC, they
yeah,
are
no, I
equal.
realized.
And one side AM is common to those of. And then, as you said, these are the same. We have another theorem which you haven't studied. This is, I want you to understand the logic we are presenting stuff here. So you are not allowed to use, we will have SSS in the future, but not now. Because then SSS is not an axiom. I should prove it for you. Yes? So this middle, even though it is correct, it is not wrong, because we will have SSS, a theorem, side from one side from the other one. But so for the time being, I cannot use that. Okay, but the idea that Hafshah actually brought up is correct. We want to have two, but the midpoint didn't work. Yes?
Should we draw like the first example and draw another triangle on the side of it?
No, I mean that this line is correct, but
No, it's
the
a bit
midpoint is not the
No, the mid.
interpretation, correct interpretation, yes? So might be I'm not very clear. I would say that I will take this and then connect it to, no, I don't say connect to the midpoint. I say draw a perpendicular line from there. Then I lose this, that they are in the middle. Of course, they will be in the middle. But what I know is that this angle is 90. Yes?
Maybe if we define this green line as the angle bisector.
Yeah, that's also good.
So then,
So, yeah.
then we suddenly have two angles which we know are the same.
Yeah, so I think that is that I was thinking that this also doesn't work. Yes, do you think this will work if I draw a perpendicular line?
Well, there's
In the
nothing-
perpendicular line, I know this one is equal to that. So I know this is in common between these two triangles.
Yeah.
This side is equal to that one, but I need this angle to be equal to that angle, which I don't have. I have another angle equal to another angle. So it's not enough to conclude. I think what Rasmus says is correct. Yes.
Yeah, well, yeah, it's not also not given that that line even will intersect with A, right? Is that given by the theorem? Like the perpendicular, is it? Because if it's
No. If I have this one, I can draw a line perpendicular to this one. Of course, this is also an axiom.
Yeah.
And why we can do that? Yes.
okay.
Yes, you're right. So angle bisector is also, if you want to be really strict, you have to understand what are the exact axioms. Okay. But let us not make things very hard. Yes, you are. So, but I want to tell you that even though this is the same line that Hafshah mentioned, but if I say that I connect this to the midpoint, I will not be able to use my axiom. But if I say that I draw the bisector of this angle, then I know that this angle A1 and the angle A2 are the same. Yes? And then look at this triangle here and that triangle here. This side is equal to that side because this is an isosceles triangle. This is my premise. And by construction, angle A1, so AB is equal to AC. Angle A1 is equal to angle A2. And we also know that whatever I call it, what I don't know, you can call it D, AD is also equal to AD. That's a side in common. But the important thing is that this angle is the angle between the corresponding sides. So this is exactly SAS. And I can conclude that triangle ABD is congruent. If I want to respect the order, I write ACD. If two triangles are congruent, then I can conclude that this angle in the middle matches this angle in the middle. So this angle B is equal to angle C. Yes? And an immediate consequence of this is that in an equilateral triangle, all angles are 60 degrees. Why? If I have an equilateral triangle,
Is that also an axiom?
pardon?
Is that also an axiom? I mean, if you have three equal angles and you know they have to be 180, it's
It's not an axiom, but that is a consequence of that. Because when you say I have an equilateral triangle, by the way, you can read this theorem in a different way. You can say that if I have two sides equal, then the angle opposite to this side should match to the angle opposite to this side. Okay? Now, if I have an equilateral triangle, it means that I have a triangle so that all sides are equal. So if I call them ABC, because AB is equal to AC, I can use that theorem to say that angle B and angle C are the same. Now let us give the role of the apex to this one. Because this side is equal to that side, this angle opposite to this, which is A, is equal to the angle opposite to this, which is C. So it means that on the one hand, B is equal to C, on the other hand, A is equal to C. So all these angles should be the same. And because the sum is 180, each one of them should be 60. Yes, is that understandable? Okay. So now you know the proof. So the validity of this argument really depends on this axiom SAS. Yes.
So I just with that triangle.
Yes.
I mean, isn't it like the definition of that triangle is that the angles are equal?
No, the definition is that the sides are equal.
No, the sides are equal.
But the consequence of the sides being equal are the angles are equal. Yes? Okay, now, of course, you have an intuitive idea. We want to make things interesting. So what happens if I do not have the sides the same size? The same sizes. So for example, I know that I have a triangle like this. Intuitively, everything seems right. So if AB and C is a scaling triangle, whatever it is, but this time my premise is that AB is less than AC. Okay? Of course, what can you conclude about the angles? What can you say about the sizes of these two angles? If I know that AB is shorter than AC. Yes, Afshin?
B is greater than C.
B is greater than C, yes? Angle B, okay, so let us write it clear. Angle B is greater than angle C. Yes? But why? We want to prove now everything. So why this is true? Okay, so you need to be a little bit experienced here. Okay, what we do is that because AC is longer than AB, I hope that you agree with me that somewhere on this line segment, I can find a point D so that the length of AD becomes equal to the length of AB. And this is possible. You put the needle of the compass here, open it, so that it is of a length AB, and then draw an arc. When you intersect, you get that one. So you need to, by the way, if you want to write it, you have to whenever you add something to the real picture, you have to write a sentence for it. So I would say that let D be a point on AC so that AB is equal to AD. Yes? So you have to write something. If you add something to the picture, even in the more complicated problems, you really have to write a lot of sentences describing everything that you are doing. Okay, do you think what will be my next part? What would be my next step? What do you think? Yes?
Well, I mean, I guess drawing a line from B to D.
B to D, yes. So we join B to D. And we join B to D. Okay, so you have to explain these things. Okay, now I think it is very clear. Can you tell me why this is the case? Now, how can I convince you that angle B is greater than angle C? So let me give you this. I want to keep it simple, but you really, if you want to write the formal proof, you have to write everything. So let me consider this part A. Let me use Greek letters. Alpha, beta, and then this angle. What do you think I can call this angle?
Alpha.
Alpha, yes, because now this triangle is an isosceles triangle. So if I call this part alpha, I should be able to call this one alpha as well. Yes? But now, alpha, what is the relation between alpha and C? Which one is greater than the other one?
Alpha is greater than C.
Alpha is greater than C. Why? Alpha, so I just want to write it orally, but I'm explaining everything. In the written exam, you have to explain everything in words. So alpha is greater than angle C. Why? Yes?
Because alpha is equal to beta plus C.
Plus C. It's an exterior angle. This alpha is an exterior angle for this narrow triangle. Yes? So alpha, we know that it is equal to beta plus C. So it means that this is definitely greater than C alone. Yes? So alpha is beta plus C, but this is greater than C alone. So alpha is greater than C. But what can you say about the size of the angle B and size of angle alpha? Alpha is part of the whole angle B, so B is also greater than alpha. Okay, so angle B is greater than alpha. Alpha is greater than C. So what you can conclude is that angle B is greater than angle C. Yes? You need to fill up the gaps if this is a written exam. You need to express things in word properly. But I want to save some time, so that's what I'm just writing it in a bit slow. Is that clear? Now, what do you think about the converse theorem? The converse implication. Is it also true or false? If it is true, it's also a theorem, yes? That's one theorem. So let us express this theorem in words. If I have a triangle, so one side is smaller than the other side, then the angle opposite to the smaller side is also smaller than the angle opposite to the longer side. If you want to express it in words, yes? Okay, now, what do you think will happen? Do you think I can go back, and if someone tells me the angle B is greater than angle C, do you still believe that I can conclude the side opposite to B, which is AC, is also greater than AB? Do you think this is also true? Intuitively, true or false? It's true. But so we cannot say it because it's intuitively true, it's mathematically true as well. Yes? So, but do you think you have a proof for that? This is very simple, but teaching you a lot of things.
Do we have a triangle? Like, do we have that? Like a
You can imagine, you can draw any triangle, but of course you know that your lines of arguments, it should be independent of the details of the shape that you draw. Yes. Okay, let me tell you something. Whenever I want to teach this, I will teach you something in numbers, yes? If you have an odd number, what can you conclude about its square? Is it odd or even?
Odd.
If you have an odd number, for example 5, and you square it, it becomes 25, it becomes odd. Of course, this is an example, that's not a proof. But let us check another thing. If I have 3 to the power of 2, 3 is odd. 3 to the power of 2 is 9, 9 is also odd. But do you think it's a coincidence?
No.
So how we can prove this? How we can prove that if A is odd, then A squared is odd. We need to have a definition of an odd number. What is an odd number? Yes?
Yeah, a number that can't be a number that can't be divided by 2 without including.
No, odd number.
An odd number.
Yes? 5, for example, divided by 2. Yes?
Can we use the modulo?
Yeah, somehow. Yeah, don't make it very hard, but just give it what do you mean by an odd number. What do you mean by an even number? An even number is a multiple of 2.
A number whose, when you divide, the remainder is equal to
1.
Wait, no, it shouldn't be 0 for even.
No, for even, for
Yeah.
odd. We are talking
Yeah,
about
for odd.
For odd is 1.
1.
So in principle means that when you say that A is odd, what do you mean? It means that A is equal to some number 2 times k plus 1. If you want to write it really formally, you have to use this quantifier. This means there exists. Yes? So there exists, I don't know, k, where in the set of, let us keep it positive, in the set of natural numbers. So this means there exists a number k belonging to the set of natural numbers such that this happens. Yes? This is the mathematical way of writing that A is odd. Is that understandable? When I say that a number is odd, it is a multiple of 2 plus 1. Is that right? Any number that is... Of course, here I also need to consider 0, yes? Because A equals to 1 is also odd, I have to consider k. So I don't know, in European school, when you say the set n, you start from 0. But in American school, which I usually use that one, in American school they start from 1. So I don't know, so you can just, so here I mean this European school. Because if I exclude 1, if I exclude 0, there is no way for me to get 1. But 1 is also odd, yes? Yes? Okay, now can you prove that A squared is odd? So what should I do? I have to square A. But you have studied the squaring rule. It becomes the first one squared, 2 times the first one times the second one, which is 4k, and then the second one squared, which is 1. But here I can factor a 2 out, even though I can factor more terms out, but I intentionally factor a 2 out. It becomes 2k squared plus 2k, and then I have plus 1. What type of number is this number if k is a natural number? I hope that you agree with me that if k is a natural number, this combination is also a natural number. So then, look, A squared is 2 times a natural number plus 1. So this means a squared is odd. Yes?
No.
But now, what about the other way around? If someone tells you a square of a number is odd, what can you say about the number itself? So you see, this was easy to show. Yes? Let me just write the converse implication. A squared is odd. Can I conclude that A itself is odd?
Yes, you can, but
That is exactly this. The way that you need to think in this problem is very, very close to the way that you need to think in that problem. Okay? I will come to you. Let me just clean the board a little bit so that gives time to others to think. Yes? First of all, I want you to understand why the same line of logic that I did for the first problem will not work here. Can you tell me? For example, here my premise, my assumption was that A is odd, so I was able to write it in that way. Then I squared it using the simple rules, and I conclude that A squared is a multiple of 2 plus 1, and then I concluded that A squared is odd. But now I have this. If I want to translate A squared is odd, this means that there exists a k in the set of natural numbers, the European schools, and so that A squared is 2k plus 1. Here, I had this assumption. I wanted to say something about A squared. It was natural to square it. But here I have A squared is odd from the beginning, so this is what I can write. But then I want to continue and conclude something regarding A itself. So the natural operation here is to take the square root, and it will spoil everything, yes? Because if I take the square root, then it becomes square root of 2k plus 1. Can I say that any number of this form is odd? No, it might be in a irrational number, yes? So I cannot say a number of this type is odd. So what is the escape? How can I escape this loophole or something? Even though this problem is very, very simple. Everyone knows that if A squared is, yeah.
well, I mean, A squared, if so A squared is odd, and we want to conclude that A is also odd.
Mm-hmm.
Well, can we do like, okay, well, A squared equals 2k plus 1 squared? Like if we assume that A is an odd number.
No, that's the point. No, that's not. That's the point. When I say that A squared is odd, what you can say is A squared is a multiple of 2 plus 1. But you cannot say it's a multiple of 2 plus 1 squared.
Okay.
Do you understand the logic? So it's not possible. So what can I do then? And I want you to understand the same line of thinking which was working for the first statement will not work here, because if I want to get some idea about A, I have only one mathematics operation that takes me from here to here, and taking the square root is the only one. But still, if I get this one, I cannot conclude because A is of this form, therefore A is odd. There is a trick, you already know about it, I have already talked about this in passing, and that is called proof by contradiction. It's really powerful, or sometimes people call it indirect proof. So the goal is to show that if A squared is odd, my goal is to show that A itself is odd. If I would say like this, if you agree with me, then we are done, we are friends. If you disagree with me, then you have to agree that A is even. So you see, this is the point. A squared is odd. I want to prove that A itself is odd. If you say no, so I would say assume that this is not the case. Let me write the format. Assume that this is not the case. and A is not odd. Okay? If A is not odd, therefore A is even. Yes? But A is even, then what does it mean? This means A is a multiple of 2. When you say that A is even, you have to admit that A is a multiple of 2. Then what happens for its square? A squared becomes 4k squared. But 4k squared can be written as 2 times 2k squared. So this means A squared is a multiple of 2. So this means that I have to admit that A squared is even. This is a contradiction with my assumption, because my assumption tells me that A squared is odd. Is that understandable? So that is a very, very strong tool when you want to prove some statements. Proof by contradiction, yes? So I assumed the negation of it, the opposite to it, and then I realized that I have to have the opposite assumption, and that's a contradiction. It contradicts what I have assumed. Yes? So then you can also prove that with this. And now can you tell me how can I prove that statement now? I hope that it is now clear. Yes? Okay. Because I want you to learn this. If you don't mind, let me write it properly. And you help me to do that. So now here, I want to prove that if angle B is greater than angle C, then side AB should be smaller than side AC. So what is the starting point? I should say that assume that this is not true. Assume that this is not the case. And AB, let me use this, I don't know, heuristic notation here. AB is not smaller than AC. Yes? My goal, we know that angle B is larger than angle C. We want to show that AB is less than AC. If you disagree, it means that AB is not less than AC. Okay, but now, if AB is not less than AC, there are only two possibilities left for these two numbers. What are the possibilities? Either AB is equal to AC, or AC is less than AB. Agree? I am claiming AB is less than AC. Okay, if you don't agree with that, you have to agree that AB is not less than AC. Then you have to admit either this one is true or that one is true. But if this one is true, what is the consequence of this one? This is still on the board, yes? If AB is equal to AC, this angle should be the same. Yes, so this means that angle B is equal to angle C. But this is contradiction. With what? With my assumption. What is my assumption? My assumption is that angle B is greater than angle C. Okay, now if you tell me this, you understand everything right. So what is the consequence of this? Don't get confused with the letters on the board. If AC is less than AB, what can I conclude about angle B and angle C based on the theorem itself?
That P is less than C.
Yes, or the C is greater than B. Is that understandable? I hope that you are not confused. You see, I have used AB and AC, but I told you read it in English sentence. This tells you that if two sides are not equal, the angle opposite to the larger one is greater than the angle opposite to the smaller one. Now, if AC is less than AB, the angle opposite to the larger one, which is C, is greater than the angle opposite to the smaller one, which is B. And that is also contradiction. Do you agree? Because in my assumption, I have angle B is larger than angle C. So if you don't accept this, then either you have to accept this, which is not true, or you have to accept this, which is not true either. Yes?
So can you prove the theorem with in that direction? Like, can you prove this without using the original theorem?
Without, that's a good question. That's exactly the same question here. I don't know. Do you have any idea how we can prove it directly? I didn't know any proof. I don't know any proof for this one directly. That's also a very interesting question. I have also thought about that. Do we have a real direct proof for saying that if a squared is odd, a is odd, without using proof by contradiction? That's more or less what I understand what you mean. So you are saying that can we prove this directly? Might be we can, I don't know. In this case, in algebraic form, I don't have any idea. Might be you can, if you have other theorems in number theory. For example, you assume that any number can be factorized in the prime numbers, you know. So might be you can use this to cook over another argument. You can also, might be, I don't know, might be instead of considering that I am choosing this in a way that this side becomes equal to that one. Here, my assumption is angle B is larger than C. Might be I draw a line. By the way, this was possible, isn't it? So let me just reverse the logic here. So this time, because this angle is supposed to be larger than this angle, then let me just do this. Yes? Okay. It is possible, but by the way, could we go to the other direction? I didn't ask you this question here. If two angles are equal, can I conclude AB is equal to AC? Intuitively, that's true. But do we have everything at our disposal to prove this right now? Because this will need that one, this direct proof, yes? Because now I would say that I will take this line so that this angle, this angle, I don't know, might be we can, because I want to make this one equal to that one, so I have to make this one equal to that one. I don't know, but I didn't ask you this question. Can we go to the other direction? If angle B is equal to angle C, can I conclude that AB is equal to AC? The answer is definitely yes, but the question is that can we prove it right now?
Proof of contradiction again. Can we use that in this case?
Okay, so I mean that this means that I have to come along all these two theorems to go back to prove it. Yes, right now probably we can go back, yes? Can we? We say that we want to prove that if angle B is equal to angle C, can I conclude that AB is equal to AC? If you want to prove it by contradiction, you say that, okay, let this not be the case. Then there are two options left. Either AB is less than AC, or AC is less than AB. But by that theorem, I know that if AB is less than AC, then angle C is less than angle B. Yes, and that's contradiction. And this one also gives me angle B is less than angle C. That's also a contradiction. Yes, that's possible. So now it is possible. So if I ask this question in the reverse order, for some reason I forgot to ask, we couldn't do that at that stage. Yes, we had to go through all these things to go back to be able to prove the other one. Is that understandable? So that's extremely important in geometry. You are learning the logic and how you need to reason so that your argument is not a circular argument. Any questions? Okay, but I want to teach you the very fundamental inequality. I don't know how many of you have heard about the triangle inequality. I don't know. Sometimes I have seen that this is a very fundamental theorem. And triangle inequality, I don't know, in Persian culture, the donkey is the symbol of being stupid, you know. And then I have seen sometimes in literature, some ancient people write that, okay, if you have a donkey here, I'm not good in drawing donkeys. And then this is the food for the donkey. And there are two paths to the food. Yes? The donkey immediately chooses this straight line to reach the food. And if donkey knows that this length is smaller than the sum of these two lengths, then let alone humans, yes? But that's not a mathematical argument for saying that this is the case. We want to prove it today. And that's a really fundamental theorem in the planar geometry, Euclidean geometry. So what is the triangle inequality? So the triangle inequality is this. So triangle inequality. So if I have a triangle, so let me just draw it in a way that I can prove it in the same picture. I have any triangle that you like. The sum of the lengths of two sides is always larger than the third one. Yes? It is not as intuitive as before, but hopefully it's also possible to understand. So I want to prove that AB, and by the way, let us make life simple. I told you the convention is that if I call it capital C, the length of the opposite side is called little c, and the same convention here and there. I want to show that if I add A to B, it becomes larger than C. If I add A to C, it becomes larger than B. And if I add B to C, it becomes larger than A. So in any triangle, the sum of the lengths of two sides is greater than the length of the third side. Yes? But how can I prove that? The proof is also interesting to see. By the way, these simple things are very hard to prove because they are so trivial, we don't know what to do with them. Yes? So how can I prove this one? I can give you a hint. So I don't know which one we want to prove. So let me see. Yeah, let me prove this one, hopefully. Yes, the third one. I would say that let us extend this side. Okay. How much? By this length. Yes, this length. So do you understand what is going on? So I extend this side, but how much? Not by the length of this side, by the length of that side. That is also possible. Why? Because I can continue this ray forever. I put the needle of the compass here, open it, and make an arc. When I get the intersection point, that point is D. And in the written exam, you have to mention everything. You should say that I extend the line segment AC so that to reach to point D, so that AD is equal to AB. I'm just telling them orally. But in written exam, you have to write everything down. It's extremely important. So AD, I chose it in a way that it becomes equal to AB. Okay? So let me write the details that I need for the future. So AD, by my construction, is equal to AB. Okay, then what? It should be clear, not hard. I join this line, this point to this. Yes? So I extend this so that AD becomes the same length as AB, and whatever I point I get as D, I join it to B. Okay. Okay, then I want to use somehow these theorems that you see on the board. Yes, I want to use this theorem. But how? Let us not get confused. If I call this angle alpha, one of the other angles is also alpha. Which one is that?
One of D.
Yes, this is also alpha because this and that are the same size. Okay? And now what you see is that what about this angle? Is it bigger than alpha or smaller? It's bigger than alpha. Yes? Now look at the bigger triangle. In the triangle in the triangle BCD, what you have? You have angle D, you have angle, let me call it DBC. Angle DBC is larger than the angle D. Do you agree? Why is that? Because if this is alpha, this is also alpha. But alpha here is just one part of the bigger angle. So alpha is definitely smaller than this angle. So this means that this angle is also smaller than that angle. Now look at the bigger triangle. Momentarily forget about this middle line. In this bigger triangle, you have one angle larger than the other angle. So it means the side opposite to the bigger angle is also larger than the side opposite to the smaller angle. Yes or no? Okay, but can you tell me what is the side opposite to the larger angle? What is the name of that side?
It's DC.
It's DC. Yes? So this means that DC is larger than which side?
BC.
BC. Agree? But what is DC? Look at the picture. DC it consists of two parts. You can write DA plus AC. If you look, DA plus AC is the same as DC. Is larger than BC. But now look, what is another name for DA? By my construction, DA has the same length as AB. But the length of AB is little c. So instead of DA, I can put little c. And instead of AC, I can put little b. And instead of BC, I can put little a. And then I've proved that. Yes? So this means that from now on, I really recommend you, if you want to practice a little bit more, try to draw the same triangle, but this time prove this one. And if you think you need, you can also prove this one. But the ideas are the same. You have to extend other arms. Yes? Yes.
This is maybe a bit more of a general question, but I've just been thinking about, we have these intuitive ideas about maths, and we think something, and this proof isn't really what, when you conclude, we know that, we can guess that C plus B is larger than A, but this isn't really the way we would think about it in our heads. We just know it instinctively. Is it like a proof that can, is it like a proof that can somehow, I know this intuitively, because I wouldn't really explain it. How do we know it intuitively? Isn't there? This might be a weird question.
No, I understand what is your concern, but sometimes we really don't have that intuition.
Yeah.
In geometry, somehow we evolved in a way, we have some ideas about Euclidean geometry around us. But the point of mathematics is to free yourself from those intuitions. Those intuitions are helpful, and it has been the source of motivation for a lot of inventions and discoveries in mathematics. But the point is that at the end, mathematics should be free of those intuitions. At the end, it should be a pure logic. And of course, sometimes we really don't have that intuition at all. So for example, the famous example that comes to my mind is probably Fermat's last theorem that took mathematicians 300 years to discover, And if you read a little bit history of that, mathematicians in the middle of the way actually split it into two categories. One group believed that this is not true. They were trying to find a counterexample, and the other were actually trying to prove that this is true. Yes? And then it turns out that both of them are hard work, because even the counterexample was not that very clear what it should be. So I mean that, yeah, somehow they are actually different things. But there are, I don't have that example right now in my head, but sometimes you have something counterintuitive. For example, in the example that I mentioned, by the way, of probably we'll talk about that polygons next time. But so here, if you remember when I was talking about this, might be your intuition was that this is interior angle.
Yeah.
But if we wanted to stick to a definition, we have to admit that this is not a good definition. The other one in this case will be the interior angle, or it would be more consistent if we define that one to be an interior angle. I don't know if I could answer somehow your question.
Well, I mean, in that case, when that is the interior angle, I mean, there's something still like you can guess that like intuitively somewhat, like, or it's like it's logical in like the same way that your intuition.
It was not it was logical, but not intuitive.
Yeah, it wasn't intuitive, but it's like if you like have the shape where it's not intersecting anywhere.
Yes, that was intuitively and logically coinciding.
Yeah, exactly.
But this picture was logically true, but probably not intuitively clear.
Yeah.
So, but is that your question? The question was the other one.
Well, no. Yeah, I think.
Yeah, something like that. I mean, so I mean that the priority is with logic, pure logic in mathematics. Yes, but of course we shouldn't underestimate the role of intuition. Yes. Okay. And this is why some people are good in geometry. For example, algebra is really abstract. Okay, so you have to have pure logic there. So some people prefer to study geometry as a branch of mathematics rather than pure algebra. In pure algebra, you don't have that kind of intuition using pictures, you know. And it turns out that both of them are very good because, for example, we can prove a lot of theorems in algebra, which is abstract, using our intuition in geometry and connect the ideas in geometry to algebra. And that is very, very famous. For example, that's an ancient Greek problem that, okay, I will talk about these things later. If I give you an angle, you can use the compass and the ruler, not educated ruler, not graduated ruler, just a ruler. Yes? So you can draw a line that bisects this angle. Yes, it's possible. And then ancient Greek actually were thinking about, can I do the same thing and trisect the angle? That's also an ancient problem in mathematics. So it means that is it always possible using the compass and just a stick without calibrating it? Is it possible to always, for any angle, draw two lines so that this becomes alpha, alpha, and alpha? For example, for the case of 135, we can do that because we already know how to draw 45-degree angle. Yes? Well, I don't know. For example, you make a square and then connect this. This is automatically 45. And you can do it one on this side, one on that side. You get 145 from this direction, 145 from that direction, and then what is left over is also 45. So it means that you were able to trisect this. But I'm talking in general. Is it possible in general to trisect any given angle? It turns out to be no. And then it is not possible, but the proof is very interesting. The proof comes from a very abstract part of mathematics called Galois theory. And that is completely in group theory. Yes?
So it's not possible to...
No, it's not possible.
Three equal angles in a
It is not possible to trisect in any given angle by the tools that I mentioned into three equal parts. But there are exceptions. Exactly 135 is one of them. I can immediately trisect it. Because this square, I can draw it with compass and ruler. Yes? That's not hard. So then I can make a 45 degrees angle. I can make a 40 degrees angle here, and I can do another one here. What is left over is also 45, if my angle is 135. But in general, I cannot do that. But in general, I can always bisect.
Yeah.
That's always true. Whatever you give me the angle, regardless of the size, I can always bisect it in two equal parts. That's also one thing. So these things, you have to be really genius, because you need to broaden your perspective to connect two branches of mathematics to prove one single problem. That problem was in geometry. Some people were working on some abstract notions. I cannot talk about them that much right now, but that is not having it, in principle, that doesn't have anything to do with shapes and figures. Of course, symmetry is also some cornerstone in that group theory. But using those tools, people were able to show that, okay, the consequence of this theorem in algebra is that this is not possible in geometry. Okay, these kind of things, you have to be really genius to be able to connect two different branches of mathematics together by one theorem or something like that. Yes? Okay. So now, from now on, we know that the sum of two sides is always larger than the other side. Okay, before finishing this, let me ask you, what do you think about the difference? I haven't talked about the difference. For example, let us consider this one. We know that if I add the length of B to the length of this, it's always larger than C, larger than the third one. But what do you think if I subtract these two? Of course, if I subtract them, sometimes it becomes negative, yes? But no, let us consider I put the bigger one first minus the smaller one, which becomes always a positive number. Then I want to compare it to the third one. Can I say something completely clear all the time, or it depends to the situation? So for example, in this picture, apparently B is longer than C. My question is that, if I subtract C from B and compare this number with A, what do you think? Is there any nice relation between these two numbers, or it depends to the situation and the details of the shape? Yes?
A should be greater than B minus.
Intuitively, it seems in this picture, yes. But do you think this is always true, or it depends to the detail of the shape of that particular triangle that you are looking at? It's on the board. It's not hard.
Well, it's always. I'm just gonna guess it's always true.
It's always true. So what you are claiming? You are claiming that B minus C is always smaller than A.
Yeah.
Yes? But it is on the board. Can you see it? Yes?
There, you said that B plus C is greater than A.
Yes?
So if you take away C, then it would give that B is...
No, if I take away C from here, this gives me B, then I have to take C away from this one as well.
Yes, so you get...
Yeah, this one is the middle one written in the disguised form.
Oh, yeah.
That's the same thing, yes? So your idea is correct. Take C away from this and that. If A plus C is larger than B, then A plus C minus C is larger than B minus C. Do you agree? And then this C and C are cancelled, so A is larger than B minus C. That's exactly the same thing written. So remember that. Okay, so this is important to know.
And is that the proof?
Yes, that's the proof. That's the proof, because that's the proof not in the realm of geometry, in the realm of algebra.
Yeah.
Because if I have these two numbers larger than, the sum of these two numbers is larger than B, this is a property of inequalities in algebra that I can do this. Yes?
But you can prove that with geometry, right?
Yes. No, we didn't prove this by geometry. We proved this one by geometry, this one and this one by geometry. Similarly. Yes? And then using an algebraic property of inequalities, I was able to conclude this one as well.
Can you do it the other way? Can you prove that with geometry? And then prove that the other one?
No, that is also an interesting question. We will talk about that later. So the question is that if I give you 3 numbers, is it always guaranteed that you can have a triangle whose sides are exactly those 3 numbers? So for example, 1, 2, and 5. Can you draw a triangle whose sides are 1 centimeters, 2 centimeters, and 5 centimeters? Okay, we will talk about these things later because it would be late. But let me just conclude this section by this. So the sum of 2 sides is always greater than the third, but the difference of any 2 sides is always less than the other one. Of course, there is nothing interesting if this turns out to be negative. If this turns out to be negative, a negative number is always smaller than 1. So, but can I say absolute value of b minus c is always less than a? You know the absolute value or not? So absolute value is the magnitude of the number, yes? So when I say absolute value of b minus c, do you accept that this is true? Yes, because from this one, a plus c larger than b, I can move this to the other side. A becomes larger than b minus c on the one hand. And from here, a plus b greater than c, I can move b to the other side and conclude that a is larger than c minus b. So I will come to you. So you see that a is greater than b minus c and c minus b. So it means that from these two, I can conclude that b minus c absolute value, a is always larger than the absolute value, regardless of which one is greater. So you see that we can write something like this. I can say that a, on the one hand, is smaller than the sum. On the other hand, is greater than the absolute value of the difference. So in any triangle, the size of any side is smaller than the sum of the other ones, but it is greater than the absolute value of the difference. So b is smaller than a plus c. It is greater than a minus c. And then c is finally less than b plus c, and then it is greater than what? Absolute value of b minus. I am making a mistake here, yes. It's a plus b, and then this is a minus b. So this is, I want you to have somewhere in your memory this inequality. This is extremely important. So what is the theorem? The theorem tells you that in any triangle, all these inequalities hold. Yes? Yeah. On any given triangle, all these inequalities hold. Yes?
Doesn't that just prove that you can't make a triangle with any 3 numbers? Because
you can have what?
You said can you make a triangle with any 3 given numbers? Mm-hmm. Doesn't this just prove that you can't? Because you can definitely find 2 numbers b, c.
Exactly. Yeah. So that's exactly it. So I want to talk about this in more depth later. This is why I don't want to talk. But you are right, exactly. If I give you any triple of numbers, if they don't follow this, it means that they cannot make a triangle. Yes. So in any triangle, all these 6 inequalities should hold, and this one part of it actually is called the triangle inequality. That is a consequence of the triangle inequality. So the triangle inequality is this, or in words, you should say the sum of the length of 2 sides in a triangle is always greater than the third. And it cannot be equal either. So if it is going to be equal, then this triangle is called a degenerate triangle, yes? So the sum if you have a real triangle, equality cannot hold. Yes, but for numbers, we will see that sometimes it holds. Then this is the case. Okay, any questions? No? Okay, so I will stop here, but I know that there is one problem left, and I want to at some point come back and talk about that polygon. So because I and Oscar, and I don't know how many of you thought about this, but I, Oscar, and Rasmus were thinking about it. We found a way to understand it a little bit better. I also uploaded some file. I don't know how many of you seen that. That's an old paper related to these things. Okay, we will talk about them later. Any questions? Thank you.